Hello friends, in this video let us discuss wave winding. In our last video we have discussed the lap winding, and in the lap winding we have seen that suppose if I say there are two singleton coils here, so this red color portion shows you the starting side of coil and this green color dotted portion shows you the finished side of the coil. So one is in the top position and this will be in the bottom position. Again I am having another coil, same, this is the starting side and this is the finishing side. So here you can see the finishing side of first coil is connected to the starting side of the next coil, and this starting side of next coil is aligned backward. So there is a backward alignment of this coil side of the next coil, that is the second coil. But here in the, this is your lap winding. Now here in the wave winding, you can see this is the starting side of coil and this is the finished side of the coil. So here also the finished side of coil is connected to the starting side of another coil, but this starting side of coil is in the forward direction. It is in the forward direction, but here it is in the backward direction, making an overlap. That is why we call it as lap winding. But here the starting side of the next coil is connected in the forward direction, and you can see this. Again here you will be having its closing end, and this winding appears or it looks like a wavy shape. So the shape of the winding appears to be wavy, and therefore this winding name is regarded as a wave winding, because this is a wave, this is like this is another wave. So as the winding shape looks like wavy, it is called as a wavy winding. And here you can see the starting side of one coil overlaps with the another coil, and successively there will be overlapping takes place in the lap winding. So you can see there will be the alternate backward direction and forward direction, backward direction and forward direction. This is going backward direction and this is going forward direction. That is, the starting side will be going backward direction and the finished side will be going forward direction, and again same with the next coils. So there is an alternate back and forth direction here. But in the wave winding, the winding progresses continuously forward, passing successfully every north and south pole. So there will be a north pole here and there will be a south pole here, there will be a north pole here and there will be a south pole to its finished side. So likewise the winding passes successively every alternate north and south pole till it comes to its starting point. Till it comes to its starting point, the winding progresses forward in the single direction, unlike your lap winding which is having the alternate directions. So here we shall talk about the two important terms. One is the progressive wave winding and other one is the retrogressive wave winding. Retrogressive wave winding. So in the progressive wave winding, after one round of armature core, so let me say this is your armature core. So you have started from this point. Now after one round of armature core, if you reach to the right side of this starting point, then your winding can be termed as the progressive wave winding. And similarly, after one round of the armature core, and if you come to this point, if your winding comes to this point which is left to the starting point, then it is called as a regressive wave winding. So here if I draw it like this, so let me say there is a winding here and this winding is coming like this, and let me say this is the, so after traveling one round of complete armature core, your winding falls in the slot which is right to the starting point. So this is your starting point and you are falling here. So as it is right to the starting point, then you can term this winding as a progressive winding. Now similarly you might be having the other windings where, let me say this is the other winding you are having. So if after traveling one round of armature core and your winding falls in a slot which is left to the starting point, when it falls left to the starting point, then this can be regarded as your retrogressive wave winding. So these are the two terms you have to remember, whether to know it is a progressive wave winding or the retrogressive wave winding. And here you can see the number of parallel paths. So the Y parallel paths in the lap winding will be simply multiplicity of the winding into the number of poles, but here in the wave winding the number of parallel paths will be equal to the multiplicity of winding into 2. So into 2, where m is equal to 1 for the simplex wave winding, it will be 2 for the duplex, and it will be 3 for the triplex, 4 for the quadruplex windings. So you can see, irrespective of the number of poles, whatever be the number of poles, the parallel paths will be equal to 2m. So it is not dependent on the poles, and you can see for these two parallel paths, each parallel path having the conductors which are more or less uniformly distributed around the circumference of this core. So there will be two parallel paths, and each parallel path will be having a number of conductors which are uniformly, more or less you can say, they are uniformly distributed around the entire circumference of this armature core. And this uniform distribution of the conductor in two parallel paths around the armature core adds you two advantages. It gives you two advantages. So let me talk the advantages one by one. So generally, the simplex wave wound DC machine can have only two brushes. It can have only two brushes irrespective of the number of poles. But for the satisfactory performance of the commutation, the number of brushes must be equal to the number of poles. So here you can have only two brushes. It's okay for you to have the commutation, but when you have the number of brushes is equal to number of poles, you will be having more satisfactory commutation of the coils. So in a wave wound machine where the number of brushes is equal to number of poles, if one or more brushes makes poor contact with the commutator segments, then also you can have the satisfactory performance of the commutation. So this is one advantage. Though you are having poor contact of one or more brushes with the commutator segments, you will be having a very good commutation, but this doesn't happen in your lap winding. So this is one advantage of these two parallel paths distributed uniformly around the circumference of the armature core. Now the second advantage is, so in the lap winding we have seen that there is a need of the equalizer connection, because the potential in several paths will be different because of the we have talked about it. One reason is the variation in the gap length, the other reason is the steel properties, that is the magnetic steel property, and the other reason is the resistance of each path may not be same. Because of those reasons, there we are having different potential in different parallel paths, so therefore we are having circulating currents. But here, as there are two parallel paths and they are distributed uniformly, so if I say a case, let me say, if the flux produced by the poles is not exactly equal by all poles, one pole is producing some more flux, one pole is producing less flux. So when they are having unequal fluxes, then your EMF in the parallel paths must differ. But here, the voltages in the parallel paths, if I say there is a 5 volt here, then there are also 5 volt here, irrespective of the unequal fluxes, because whenever you are having some differences in the flux or differences in the induced EMF, it will affect both the parallel paths similarly. So as the effect is on both the parallel paths similar, suppose due to the unequal fluxes, the effect here it is, let me say there is a 4.8 volts, and similarly it will be also having 4.8 volts. So the potential across these two parallel paths is maintained constant irrespective of the fluxes differences. So that is the other advantages of providing the sparkless commutation, and here brushes we are having good commutation. So these are the two advantages of these two parallel paths having conductors uniformly distributed around the armature core. Now, as we are having only two parallel paths, this machine is suitable for the high voltage and low current machines. Where you require high voltage, then you can employ this wave winding, because it is having only two parallel paths, and all the EMFs will get added here. But in in the lap winding where the number of parallel paths will be equal to m into p. So there the lap winding is employed for low voltage and high current machines, because we are having a number of parallel paths, so that you can obtain a high value of current. But here we are having only two parallel paths, so there will be less current, but you can have more voltage. So that is high voltage, low current. Now if I say I am having a 125 kilowatt machine and it gives you current of, total current rating is 500 ampere. Then each parallel path will be having the current of 250 amperes and other one is having of 250 amperes. Now this 250 ampere is very high, or you can say it is a limit, current limit to be carried by a parallel path. So in such cases, it is customary to employ, or you can say it is usual in practice to employ the simplex lap winding. Simplex lap winding, but in order to retain the advantages offered by your wave winding, that is the commutation and the sparkless commutation what we have discussed. So in order to retain those advantages, we can go for the multiplex winding. So in the multiplex winding, you can have the increased parallel path. So when you have increased parallel path, you can go for the higher current rating. But this increased parallel path will provide some, it will render some operating difficulties. So because of that reason, we are not going for the multiplex wave winding, but we are simply going for the lap winding when we require high current. So now here later on I will talk about the important points regarding this lap wave winding. One is the simplex wave winding and other one is the multiplex wave winding. So first let us proceed with simplex wave winding. So I will talk the important points regarding simplex wave winding. So the first point is, here your back pitch and the front pitch must be odd. So this is one point. So here if I tell you about the back pitch and the front pitch, I have already discussed in my lap winding clearly, but here I will say, so your back pitch is nothing but the coil span, which is the distance in terms of the armature conductors between the start side and the finish side. This is your YB, and the finish side, and the distance between the finish side of one coil to the start side of another coil is your YF, and the start side of one coil to the start side of another coil is your YR. This is your Y resultant. So the first point is the back pitch and the front pitch must be odd, and the second point is the back pitch and the front pitch must be nearly equal to the pole pitch. Your YF must be nearly equal to pole pitch, which is nothing but the total number of conductors per pole, and it must be nearly equal, or you can say they may be equal, and in case they also may differ by 2. They also differ by 2. Now when they differ by 2, your back pitch will be given by Y average plus 1 and your front pitch will be given by Y average minus 1. So this is the second point. And the third point is the commutator pitch. The commutator pitch is nothing but the distance in terms of commutator segments between the two ends of a coil. Two ends, that is the starting end of a coil and the finishing end of a coil. So this will give you the commutator pitch. So here your commutator pitch must be equal to the average pitch, and your average pitch can be given by YB plus YF by 2, and this also can be given by Z upon P plus or minus 2M, where M is equal to 1 for the simplex wave winding. Now why we have considered this plus or minus 2 here? So the reason for considering the plus or minus 2 is the winding must close itself, the wave winding must close itself without, the wave winding must close itself with including all the coil sides. So if you do not consider this plus or minus 2 and you simply take Z upon P, then the wave winding may close itself without including the coil sides, or you can say the wave winding may fall 2 conductors short to reach the starting point. So the wave winding must come and reach this starting point, and it won't be short of any conductors, or it won't be more of any conductors. When you are having more conductors, you can make them as dummy coils. I shall talk about it, dummy coils. So the conductors should not be short of the two conductors, and the wave winding must close itself including all the coil sides. So all the coil sides around the circumference of the armature must be included, and such that the wave winding may close itself including all the coil sides. So, and this average pitch must be a whole number so that the winding may close itself including all the coil sides. So it must be a whole number. Now let me consider a machine. Let me consider a 4-pole machine. I am having a 4-pole machine with 28 conductors. Now when you are having a 4-pole machine with 28 conductors, your Y average will be given by simply it will be 28 plus or minus 2 upon 4. Now this will give you result 28 plus 2 is 30, so it will be equal to 7 1 by 2, and 28 minus 2 it is 26, so it will be equal to 6 1 by 2. So this is a fractional average pitch, and for the wave winding to close itself it must be a whole number. Now how can we get that whole number? So if you consider the conductors to be 26 or 30, you will get the whole number, that is Y average will be equal to, if I say 26 plus or minus 2 upon 4, where plus is for the progressive wave winding and minus is for the retrogressive wave winding. So it will give you 28 by 4 as well as 24 by 4. So this is 7 and this is 6. So your Y average you are getting as a whole number here by considering the 26 conductors only, and the 2 conductors can be made dummy coils. The 2 conductors can be made dummy coils. I will talk about it. So that means you have to incorporate the average pitch to be a whole number, and this machine cannot be worn for any number of conductors. So for any number of conductors this machine cannot be worn, and you have to be selective while choosing the number of conductors so that your Y average must be a whole number. When Y average is a whole number, you can have the winding closes itself including all the coil sides. So this is what we mean from the Y average. And the 5th point I shall talk about is, so let me consider under the 5th point, for even number of poles. For even number of pole pairs, let me say 2, 4, 6. So when I say 2 pole pairs, that means you are having 4 poles. When I say 4 pole pairs, you are having 8. This is 12 poles. So for when you are talking about the even pole pairs in the simplex wave winding, so here your Y average it can be odd or even. So it can be odd or even, and your coils must be odd and your commutator segments must be odd. So this is the winding calculations, and for odd number of poles, that is 1 pole pair, odd number of pole pairs, this is even number of pole pairs. For odd number of pole pairs, 1, 3, 5. So 1 pole pair means you are having 2 conductors. This is 6 and this is 10 poles. 2 poles, 6 poles, 10 poles. For odd number of pole pairs, here your coil can be odd or even. The number of coils can be odd or even, and the number of commutator segments can also be odd or even. And if you are having a odd number of coils, then your Y average should be even, and you are having a even number of coils, then your Y average should be odd. So this is about the simplex wave winding. Now let me consider the second case is the multiplex wave winding. So the multiplex wave winding, the relation between the front pitch and the back pitch will be similar to the multiplex lap winding. So in the multiplex wave winding, the relation we are having is YB is equal to YF plus or minus 2M, where M is equal to the multiplicity of the winding, and I have told you 1 for the simplex, 2 for the duplex, 3 for the triplex. So this is one relation, and the other relation is the Y average here, it will be simply equal to Z plus or minus 2M upon T. So this is about the multiplex wave winding, and here I shall talk about the dummy coils. So dummy coils are required here in the wave winding, whereas equalizer connections are required in the lap winding, because in the lap winding you can see the number of parallel paths will be under one pole pair, and there will be differences in the potential of the parallel paths, and there will be circulating currents. So to make the potential equal, we use the equalizer connections, but here we go for the dummy coils and we do not require equalizer connection, as we have already talked about the advantage of having the two parallel paths of the wave winding. So the dummy coils are nothing but the inactive coils. They are nothing but inactive coils, and these dummy coils, if I say, we have talked about these 4-pole 28 conductors. Now similarly, I'll talk about the other machine. So let me say I am having a 4-pole machine with 16 slots. You are having 16 slots, and each slot will be having 2 coil sets. That means here you are having Z is equal to 32 conductors. Now when Z is equal to 32 conductors, you will be having your Y average will be equal to 32 plus or minus 2 upon 4. So this gives you some fractional number. It will give you 34 by 4, and it will give you 30 by 4. So this will be 7 1 by 2, and this will be 4 is 32 8 1 by 2. So we are getting the fractional average pitch, but your average pitch must be a whole number. So if you employ the 30 conductors, when you say Z is equal to 30, you will be having your Y average will be equal to 30 plus or minus 2 by 4. So this will be 32 by 4, and it will be 28 by 4. So this will be 8, and this will be 7. So you are having the Y average to be a whole number. So now when you are using Z is equal to 30, it is okay. You are having a whole number, but when you are using Z is equal to 32, you are having a fractional number, and these two conductors are causing a problem now, because whenever you go to the armature winding shops, there will be already standard armature punchings, and they may not be according to your requirements of the winding. So according to the requirement of your winding, you need only 30 conductors. But if you say the standard armature punchings available in the armature winding shops will be having the slots for 32 conductors. Now what you can do with these two conductors, you have to make these two conductors to be inactive, so that these two conductors won't come into picture. So for these two conductors, you tape them and you keep separated from the electrical connection, or you can say separated from any connection to the commutator segments. So as you can see, if I say there are 6 conductors useful and 2 conductors are not useful. So you will be having 6 conductors, 1 2 3 4 5 6, and these 2 conductors will be isolated electrically, and these 2 conductors will help you in maintaining the balance of the machine. Now if you do not employ these 2 conductors, then your machine won't be balanced. So what is the use of dummy coils? Then you can say, to maintain the balance of the machine, dummy coils are used, and they are inactive coils which are devoid or which are lacking any electrical connection, and they are just taped. So they are insulated from the electrical connection and they are kept inactive, and the purpose of the dummy coils is to give balance to the machine. So this is all about the wave winding, and in my next video I shall take a problem on this wave winding, and I'll finish with this winding part. So I hope you understood well. Please subscribe to the channel. Thank you.